This is the next and actually the last lecture of the geometric modeling course. Spatial partitioning is a wide class of representations with common characteristic of switching from continuous models to model discretizations. We'll cover the classification of spatial partitioning schemes and then go through particular schemes such as cell decomposition, spatial occupancy enumeration, volumetric or voxels objects, quadtrees and octrees, binary space partitioning trees, abbreviated as BSP, and ray representation. In spatial partitioning or spatial decomposition representations, a solid is decomposed into a collection of adjoining non-intersecting solids that are more primitive than the original solid. The primitives may vary in type, size, position, parameterization, and orientation depending on the particular scheme. This table gives the classification of representational schemes depending on the type of primitives. See the first row of the table. Cells in the form of cubes, prisms, and hyperpatches are used in the cell decomposition. A cube with fixed size is the only primitive of the spatial occupancy enumeration, also called the voxel representation. Cubes of variable size are used in octrees in 3D and in quadtrees in 2D. A planar half-space is the single primitive of BSP trees. And finally, line segments are primitives of the ray representation. In the cell decomposition, an object is decomposed into separate pieces, so that each piece of the final decomposition is easier to describe than the original object. Cells are primitive solids, block, prism, cylinder, for example, or parametric tricubic solids, hyperpatches. Cells do not intersect and share vertex, edge, or face. A solid is represented as a union of cells. In the shown example, a cup is decomposed mainly into cylindrical cells. A hyperpatch, or in other words, a parametric solid, is a set of points with coordinates given by continuous 3-parameter single-valued mathematical functions of the shown form. U, V, and W each belong to a unit segment. These functions, in general, map a unit cube to a curvilinear solid in space. The algebraic form of the tricubic solid is given in the upper polynomial equation. For x variable, the expression takes the form shown below. This expression has 64 coefficients, which means that the total number of coefficients for x, y, and z is 192. It means that hyperpatches in their general form are hard to handle and expensive to calculate. Composite hyperpatch solids are constructed of several hyperpatches with required continuity condition. For two hyperpatch solids, the C0 continuity condition means that they share the same surface patch as a face of contact, and the C1 continuity condition means that the derivatives by one of parameters are equal at the shared face as illustrated by the image. Spatial occupancy enumeration is a special case of cell decomposition with identical cells arranged in a fixed regular grid. The cells are often called voxels. The most common cell type is the cube, and the representation of space as a regular array of cubes is also called a cuboidal, shown on the slide. For every cell, only its presence marked by 1 or absence marked by 0 in the grid is defined. A cell is presented in the grid if it is occupied by the object. Set-theoretic operations can be easily implemented because at each cell one can apply just a corresponding Boolean logic operation. Disadvantages of this representation are quite serious. It is an approximate model, and no concept of partial occupancy is available such that a cell can be either completely empty or completely full. These models are quite memory-consuming, occupying up to n to power 3 cells, where n is the number of cells along one axis. Volumetric objects are extensions of spatial occupancy enumeration. Some numerical values are defined in the nodes of 3D grids. It can be density, temperature, pressure, and so on. The modeled object is usually defined by the positive values. We can see of this model as a set of parallel cross-sections with a 2D grid in each of them, as shown on the slide. Then, the data set can be thought as a pile of 2D matrices. Sources of volumetric data are computer tomography, as shown in the image, numerical simulation, manual sculpturing, which is a kind of 3D drawing with a brush, and voxelization of geometric primitives, where at each node of the 3D grid we can assign either a real value for the implicit form or at least binary values for the nodes with non-negative functions values as shown at the bottom. One of the applications of voxel models is volume graphics. The data flow of volume graphics is shown on the slide. The major sources of volumetric data displayed at the top. These are sampled data from measurements or simulation on the left, and geometric models on the right. The sampled computed input are 3D reconstructed to fill gaps of missing information and then are stored in the volume array. The geometric model in 3D continuous space is represented by geometric formula, which is 3D scan converted, voxelized into a set of voxels that best approximate the model and is stored into the volume array. Then, the volume array or the volume buffer is used to render an image stored in the frame buffer shown at the bottom. Octrees are a hierarchical variant of spatial occupancy enumeration. Octrees are derived from quadtrees, a 2D image representation. The image shows an object represented using spatial occupancy enumeration at the left and quadtree at the right. A quadtree is derived by recurrently subdividing a 2D plane in both directions to form quadrants. As soon as a rectangle is completely empty or completely full, it is marked as so and is not subdivided further anymore. Note the big empty area in the center of the right image. Let us see how the quadtree data structure is organized. We should give the minimal cell size, and when it is reached, subdivisions stop. The root of the tree represents the entire object. Then, it is divided into 4 quadrants, numbered as it's shown at the top of the tree. The root has 4 subtrees corresponding to the 4 quadrants. The quadrant is full if all of the smallest cell in the intersect of the object. This happens with the upper right quadrant, number 3. So, it is marked as full, shown by black node in the tree, rightmost node, and is not subdivided anymore. Other quadrants are subdivided, each in 4 quadrants again. The quadrants are checked for being full or empty. Note the quadrant 3 of the second layer of the initial quadrant 0, marked as empty, and shown as a white square. Set operations are a little more complex with quadtrees than with regular grids. For example, 2 quadtree objects, A and B, are shown on the top. Their union is shown at the lower left, and the intersection at the lower right. Note that we need to remake the entire data structure for the result of the operation. An octree is one of the 3D spatial partitioning schemes, and it is an one-dimension higher version of a quadtree. An octree construction procedure divides regions of 3D space, usually cubes, into octants and stores 8 data elements in each node of the tree, numbered as shown in the image. The procedure tests each octant, and octant subdivisions continue until octants are homogeneous, full or empty. The number of nodes in an octree is proportional to the object's surface. It is a big advantage compared with the regular grid, where the number of voxels is proportional to the object volume. The operations supported for octrees are Boolean operations, rotation by 90 degrees, scaling by powers of 2, and translations. There is a problem of aliasing of the octree objects under general transformation, like arbitrary rotation. See an example on the slide. This example of an octree data structure is similar to the previous quadtree examples. The difference is that the root and each node has 8 children. The nodes of the octants that are completely full or empty do not have children nodes. See, the 7 of 8 octants of the first level are not subdivided. It provides very good memory compression compared with regular grids. BSP trees recursively divide spaces into pairs of subspaces, each separated by a plane of arbitrary orientation and position. Each internal node of the BSP tree is associated with a plane and has 2 child pointers, one for each side of the plane. If the half space on a side of the plane is homogeneous, then its child is a leaf and represents a region either inside in or outside out the object. The construction of a BSP tree requires a single geometric operation, which partitions a convex region by a plane as shown in the top image. It also needs a single combinatorial operation, which adds 2 children to a node as leaves of the tree, as shown by the lower image. A BSP tree can represent an arbitrary concave polyhedral solid with holes as a union of convex in regions. An example shows a BSP tree representation in 2D. The left image is a concave polygon bounded by black lines. In addition, it has lines defining the half spaces. The right image is the corresponding BSP tree. First, look at the line A, which is at the top of the tree. It has the object on both sides, so it has 2 subtrees in the tree. It has the line G as its right child. This line has one side empty. It is marked as out in the tree and the line K on the other side. Starting from the line A, the procedure can recursively process right and left subtrees, and eventually build the entire BSP tree. This is another example of a BSP tree of the concave polygon shown at the right. The data structure requires only 6 half-plane nodes corresponding to the sides of the polygon. BSP trees can be used for inside-outside classification of closed polygons. To do so, we, of course, need to construct a BSP tree for a given polygon first. Then, we need to traverse the BSP tree for the interesting point. In the upper example, the traversing provides us with in answer. In the lower image, we come to out node in the tree. This table provides a comparison between traditional 3D spatial partitioning schemes and CSG. The main difference is that CSG is concise and can make an accurate model, while other schemes are verbose and approximate. Only BSP trees can exactly represent a big class of arbitrary polyhedra. They are also independent of orientation and have efficient rendering algorithms. The ray representation is relatively new. Just to remind you, it is based on ray grid G, that is a rectangular array of finitely spaced parallel lines. The ray wrap of a solid A is a set of G in A and G on A segments of a ray grid. A tag is a descriptive symbolic information appended to the G in A segments. All main elements of the ray representation are shown in 2D here. A regular grid of parallel rays G going through some solid object A at the left, and the ray wrap itself is an intersection between the ray grid and the solid at the right. This is the ray grid in 3D space. When it is intersected with some solid, it makes a ray representation of the solid as a set of line segments. Let us look at the interesting hardware implementation of solid representation conversions, namely the CSG to ray wrap conversion with the RayCasting Engine. It was told before to generate a ray wrap of a solid, we need to intersect a ray grid with this solid. The RayCasting Engine, RCE, is a highly parallel special-purpose computer that generates ray wraps by classifying ray grids with respect to CSG solids. The output from the RCE is a list of interval segments. Each interval in the list represents an interval of intersection between a ray and the CSG solid. This collection of interval segments is a discrete approximation of the solid. RCE hardware has to perform the following functions. First, it performs the parallel ray primitive classification with primitive classifiers. Second, RCE provides a deep pipeline to perform the upward propagation of the classification results. Classification combiners combine in segments from the left and right subtrees in accordance with the set operations in the nodes of the CSG tree. It combines classification in parallel at every level of the tree. How does the RayCasting Engine process CSG objects? A CSG tree, shown in image A, is associated with a programmable reconfigurable tree, image B. Those leaves are primitive classifier processors, marked as PC, and those nodes are classification combined processors, marked as CC. In other words, PCs represent primitives in hardware, and CCs represents set operations. However, if implemented directly, such a structure would require a different number of processors for each CSG solid. We can present any CSG tree by a right-heavy tree as shown in image C, and any right-heavy tree with n leaves can be mapped onto an n times log n plus 1 array of processors, as shown in image D. N of these processors are primitive classifiers, and others are classification combiners. These matrix of processors can intersect a grid of rays with a CSG solid very effectively. Here is the list of additional references used to prepare this lecture. Thank you for your attention, and good luck on the exam.